So Arpita Sinha is a faculty member at the Center of Systems and Control at IIT Bombay. She earned her PhD in Aerospace Engineering from IISc Bangalore in 2007 and completed postdoctoral fellowship at Cranfield University, UK, for a year before joining IIT Bombay as a professor. Her research focus lies at the intersection of robotics and control system. She is particularly interested in autonomous vehicle guidance, multi-vehicle coordination, and distributed decision making. Currently, she is working on projects related to autonomous on-road driving, UAV-UGV coordination, multiple mobile manipulators control with human in the loop. With that, I would like to invite Arpita Sinha for the talk. Thank you.
Thank you, Amit, for the introduction. And I'm audible, right? Yeah. And thank you, Ashwini, for organizing this event. It's great to be here back after 2 decades. And I still feel it was just yesterday when I joined for my PhD, and time has flown since then. So I would like to say that whatever I could achieve in so far, it was all because of my PhD supervisor, Professor Ghosh. And one of the best thing that I learned is like doing good research is not necessarily have to be juggling with complicated mathematical equations. It can, even a simple logical thinking can give nice, interesting results. So with that, I would like to talk about the work which is done by one of my students, Deepak. He's being jointly supervised by me and my colleague, Leena. So what he worked on was priority patrolling. So in that, what we have here is the patrolling problem. As we know, it's about securing maybe a building, can be a workshop floor, it can be a campus or a part of the city. So the environment, the patrol environment is what we are interested in. And what we need to do is, there are specific locations of interest which can be the entry gates or such locations like the black dots here, and we would like to have the mobile robots go around to secure this environment. So typically in the literature, we've seen that there are adversarial and non-adversarial environments. So a non-adversarial will be where the robots are not necessarily interested in catching an intruder. It's more of a deterrent, that action that is going on. So so this patrolling problem is like you have this, can be one or several of these mobile robots that are patrolling, and we decide how do they move or decide the path, and it happens round the clock. So it's a kind of an infinite horizon problem. So in this problem now, the flavor that was added was the priority patrolling. So where we have some specific locations which are of higher priority than the regular ones. So like we can have these administrative buildings and so on. Okay, I can use the, sorry. Okay, never mind. So this locations, what is important is that it should not be left unvisited for a very long time. So to formulate this problem, what we can think about is, we can define the idleness, like the time a robot visits this location, the time that has lapsed since then, we can call it as the idleness, and we can say that this idleness value should not be too large, or we can give a specific constraint, a time constraint, which we can say it as a time period. So, in this problem setting, what we can think about is that the idleness of the priority nodes, the nodes which are shown in this blue colors, for them the idleness values should not exceed the time period, which is a user defined quantity, and for all the rest it should be visited as frequently as possible. Okay. So, for this problem there are some questions that comes up, and this Deepak has tried to answer those questions. So, before going to the questions, let me formally put the problem statement, which goes like, this environment we can obviously represent it as a graph. So, this nodes, the locations would be the nodes, and the roads connecting those locations would give the edges of the graph. So, we have this graph, and on this graph there are this set S which corresponds to the priority nodes, and their time period is T. So, we need to find a strategy, a patrol strategy, which we define by this tuple. It's the node that is visited and the time instance when it is visited, and it's an infinite horizon problem. Now, we need to find this which will ensure the idleness of the priority nodes, and the idleness of the other nodes are also bounded. So, it's like they are visited frequently enough. So, the questions that we can straight away ask is, given this setup, can we define this time period which is user defined? Can it be any value? Can it be as small as we want to, given a graph and the set of priority nodes? Or there would be some bounds that this time period needs to follow. Now, suppose this the time period can be, even if the time period is reasonable, how would a feasible solution looks like given a generic graph and the priority nodes and the time period? So, will it be a kind of a recurring circuit, or will it be optimal? How will the formulation look like? What are the practical ways of finding a solution? So Deepak tried to answer these questions, where some of the results we have it and are published. There are others which are still under review. So, I will just talk about the first few problems and the last problem. So, the first problem we have solved. So, finding the bound on the time period, we worked for the single agent. The multi-agent is under review. So, for the single agent, let us look at what happens. So, let us look at this a simple case of a environment which is a ring, just a ring, and we have 8 nodes, out of which 4 are priority nodes, and the time to go from one node to the another is, say, 1 unit. So, the solution here is rather all that you can do is to go around this ring. Now, if you go around this ring, can we have a time period which is, so to go around it will take 8 units of time. So, can the time period be less than 8? if it is less than 8, there is no way that this problem has a feasible solution. So, in a way, what we can say is that the time period cannot be arbitrarily small or arbitrarily selected. But then what can be a lower bound? So, to look at that, suppose we consider a more generic case where we have the priority nodes and we try to find a path that goes through the priority nodes. So, a solution for this would be any traveling salesman problem solution that will give you a path that takes you through just the priority nodes. So, to satisfy the idleness conditions or the time period for the priority nodes, this can be an option, and the length or the time taken to cover this path can give you the lower bound for the time period. But is that enough? It will not be enough, because if you keep just doing this, you will miss out the non-priority node, visiting the non-priority nodes. So, we have to do something more than this. So, the idea that we have used here is that we take the all the priority nodes and we pick up one non-priority node, okay? And for that we decide the decide the TSP solution, okay? So, one such thing can be a path like this. The other can be a path like this. Now, we take all such paths and find the time taken to cover all such paths, the maximum time it will take. Now, if you pick up a time period which is lesser than the maximum value, so this is the set, the priority nodes plus one non-priority node, and you what you do is you find the TSP and you find the length of the TSP. So, here the assumption is that the speed of the vehicles are constant. So, when we take the max value, so any time period that you select which is lesser than that, you will not have a solution, and that is quite obvious. We can check it through contradictions. So, this gives us a lower bound on the time period for any general graph and a set of priority nodes. So, given this scenario, can we think about what can be a feasible solution? How would a feasible solution look like? So, we can see that the feasible solution would be a recurring circuit, a circuit that repeats itself. How do we see it? So, for that we need two steps. The first is the first is that idleness of all the priority nodes are finite. So, this is not very intuitive, but if you see that since the graph is finite and the time taken to go from one node to another, those time intervals are also only finite possibilities are there. Therefore, when a robot reaches a node, the idleness value can only take a finite option, because it is a feasible solution. So, it has the idleness cannot go to infinity. So, 3 points. First is that the graph is finite, the time taken to go from one node to the other is also the time requirements are finite, and the idleness is also finite. So, that would ensure that the time required, the time interval until the robot comes back can only be finite. So the idleness at the instance when a robot visits a node can only be finite. And since we are looking at an infinite horizon, if we stack the idleness values of just the priority nodes, which is given by this script I, we get a vector, and we look at this vector at the instances when the robot reaches a node. So this vector is only finite, finitely many such vectors will exist, and over the infinite horizon these vectors will repeat infinitely many times. So it's like, if you look at this node, a feasible solution would have at some time Tm a robot coming here and going off. At some other time Tn, the robot will come back to this node and go away. Now the idleness of all the other priority nodes at Tm and at Tn, it is possible that they are same, and there will be several such instances. So we pick up the instance, these two instances, when the idleness is same, and as well the nodes that are covered within this interval. So that's the node S at Tm and the node S at Tn, and all the other nodes that are visited here in between, we ensure that all the nodes are visited. If we pick up that section of the patrol strategy, this section, it can be repeated infinitely many times, and that is also a feasible solution. So a recurring solution is a feasible solution. So how is it important, or where we can use it? It's like when we try to look for a solution when you have any graph. For a generic graph, it's very difficult to give a solution. So if we can find next we show that a way by which you can find a recurring solution which will be a possible a feasible solution for the graph. Now based on that, you can compare other algorithms and compare the effectiveness of the algorithms. So I will, in the interest of time, I will not explain how we actually find for a generic graph, how we can find a recurring solution. The idea remains the same. You take the TSP over the priority nodes and include one non-priority node, and you iterate over to find the time, the circuit that gives you in the solution in minimum time. So Deepak had went further and walked up with multiple agents. This is for a single robot, for multi-robots, which I will skip. I'll be happy to discuss if anyone is interested. I'll move forward to talk about implementation that we can do in real time. So here what we have is, when you have multiple such robots and it's trying to solve the same problem, which now we put it in this form. It's a minimization of the average idleness of all the nodes in the graph, and since you have a time period, so the overshoot from the time period for just the priority nodes. So we try to minimize this. So for this, how we can have an online strategy? So one of the ways is we can define valid walks. So what is a valid walk? It's the walk between any two priority nodes. So for example, this is a valid walk. From here to here is a valid walk. So we consider all possible valid walks which have the length which is lesser than or equal to the time period. And what we would do with this valid work is we assign each robot a valid work to take, and once it has completed, it decides the next valid work to take. How do we decide which valid work to take? For that, there is a cost or a reward function which has these components. So, first term is same as the idleness, the second one is the overshoot, and then some other components, the length and the distance to other priority nodes. So, it is more of an heuristics, and you have this C1, C2, C3, C4 which are the weights, tunable weights, and as you change those weights, the performance varies as expected. So, what we do is, first in offline we can calculate all the, given a graph and the priority nodes, we can calculate all the valid works, and in online mode, as the robots complete their valid work, they select the next valid work based on the reward. So, this is the reward, and we try to maximize this, because if the robot goes through this particular path, it will this particular valid work, it will reduce the idleness to the maximum, reduce all these terms to the maximum. The problem here is that the valid works, as you can realize, as you increase the time period, the number of valid works it explodes, it increases exponentially. So, computing and storing can be a big issue. So, how we can address that has also been looked into. I will still not, I will also not go into those details. So, this is just one of the comparisons that we present in any paper to get it accepted. So, here what we see is that we have a grid like environment, and these are the 4 corner points which are the priority nodes, and there are 3 robots that has to go through, and the time period is 100, and to travel from one node to the other it takes 10 units of time. So, in this case, when we run the valid work algorithm, we get a idleness values where we see that. So, here we are comparing our results with some results available in the literature, and we see that only here it is violating some of the times, but otherwise it is kind of maintaining. I will not, so there are works that has been done further to that, I will not get into it, but I will take this opportunity to tell that about my department. So, as introduced by Amit, I am with Systems and Control Engineering. It is a center at IIT Bombay, and it is more of a postgraduate department, and we have me and Leena, we have our lab, which is the Autonomous Robots and Multi-Robot System Laboratory, where we have all the facilities, and we have some visitors, some photos are here, and we were lucky to have sir and madam visit us a couple of months back. So, I would like to take this opportunity to also welcome and encourage the current students who are graduating and has graduated to join us in SysCon. We are really looking forward for more faculties, and also I would request the other faculties who are here to encourage their students to join us. We are, yeah. So, I'll these are the publications based on which I just talked about, and thank you.
Thank you, Professor Sinha, for this talk. So, audience questions? Yeah.
You can shout, I can give you.
No, mic.
Arpita, that was a nice presentation. I have one small question. See, if the number of nodes increase, then you always suffer from that curse of dimensionality, isn't it? So how do you tackle that?
Okay, I'll just say it this way. Okay, definitely that's a big challenge. And so what we looked into is not a suboptimal solution, so that we have walked into. So it's more like a rabbit walk. So a part of it you try to optimize, and the rest, the long term, you don't optimize. You take the shortest path. Try to solve within your budget. So that is one work that is under review right now. So we'll discuss when required. And then I forgot to mention this. Another important thing that we can look into is, like, since it's an infinite horizon problem, you need to stop for refueling. So that's the other thing that, yeah.
So, nice talk, Professor. So, I have a question. So, is it assumed that all the priority nodes form a common thing? So, do you have to travel to a non-priority node to reach a priority node? Is that?
Yes, so that will depend on the graph, the
Yes.
underlying graph, which is given and fixed, and the priority nodes are predefined. Now, when you find the TSP solution, it might include some of the non-priority nodes in order to go through all the priority nodes. It can happen.
Okay, so in that case, you will always need to go through that non-priority node. So that is.
That is
That
so
will
that
be okay.
those nodes are
Okay.
lucky to
Yeah,
visit
okay.
frequently.
Okay, thank you.
Here you can use like a GPS type of sensor to cover the nodes
Yeah. So.
for navigation.
So here what we have not looked into is how we do the, so here we are more looking into the path that needs to be traveled, but while going on the path, how do we go, or how do we track that aspect? We have not touched upon. So those problems are definitely there, how we go ahead.
Any other questions? Still we have 2 minutes. Okay. If not, let us thank again Professor Sinha for the exciting talk.